All right, so what we have here is we have section 5 or lesson 5, composing and decomposing numbers, least common multiple and greatest common factor. Our learning goals are to determine the greatest common factor of two whole numbers less than or equal to 100, use greatest common factors and the distributive property to rewrite the sum of whole numbers 1 to 100, determine the least common multiple of two whole numbers less than or equal to 12. Write the prime factorization for each number. I can make a factor tree if I need to. I don't have to, though. And so I know the prime factorization for 21 is 3 times 7. For 30, we have 3 times 10 and then 2 times 5. And I know these are prime factors when they just have two factors, 1 and the number itself. All right, 42. It's going to be 6 times 7, and then it'll be 2 times 3. And then my prime factorization will be 2 times 3 times 7. And then 59 is just 59 because it is a prime factor. Number relationships are useful in solving everyday problems and in mental arithmetic. Understanding these relationships will deepen your knowledge of how the number system is structured. How can you use LCM and GCF to compose and decompose numbers? All right, and so we're breaking numbers up into different parts, and we're trying to use that to maybe understand a little bit more about problems and about the numbers themselves. All right, getting started. Beads, beads, beads. Emily has 3 bags of different types of beads. She wants to split up the beads into mixed packages. So split up is telling us something into mixed packages to share with her friends, all right? She wants each package to have exactly the same number of each type of bead with no beads left over, okay? So they're talking about splitting it up or dividing it and making sure everyone has the same amount. And when we're splitting something up, we're trying to get smaller. And so we are looking at factors. And since we're looking at factors, we're looking at common factors. And depending on how the question is stated, we are probably looking at the greatest common factor, but we'll have to read it very carefully to make sure that it's common factors or the greatest common factor. So whenever they're splitting something up or they're dividing it evenly, then we know we're using the GCF. Notice how the question says greatest than 2. What is the greatest number of packages? And so that's telling me it's the greatest common factor that Emily can assemble. Describe the collection of beads in each package. Okay, so there's spacers. And for the spacers, there's 40 of them. And so I know I could have one package of 40. I could have 2 packages of 20. I could have 4 packages of 10. I could have 5 packages of 8. Okay? Or I could flip that around. I could have 8 packages of 5, 10 packages of 4, 20 packages of 2, 40 packages of 1. The round beads, I know that there are 72 of those. And so I'm kind of listing out the factors here. 2 and 36, 3 and 24, 4 and 18, not a 5. There is a 6 there, 6 and 12, not a 7. There is an 8 there, it goes with 9, all right? And then finally the rectangular beads. And for that, there's a 24 count, so I could have 1 package of 24 or 24 packages of 1, 2 packages of 12 or 12 packages of 2 of the rectangulars, 3 packages of 8 or 8 packages of 3, 4 packages of 6 or 6 packages of 4. Okay? And so now that I have all of these possibilities for breaking them up, I want to make sure I split them up into the same amount. So I could do 1, I could do 2, I can't do 3 because it's not in all 3. I can do 4 because it is on all 3 of them. Can't do 5. It's not on all 3. Can't do 6. Can't do 8. It's not. Oh, 8 I can do. 8's in this one. 8's in this one. 8's in this one. Not 10. Not 20. Not 40. Okay. So the greatest is going to be 8. All right. And so I would say 8 packages. And then in the 8 packages, there would be, I have to look at the factor pairs here. And so if there's 8 packages, then there would be 5 spacers in each package. I look at the factor pair. There would be 9 round beads in each package. And then there would be 8 packages. There would be 3 rectangular beads in each package. So this is the greatest common factor problem. They talk about splitting it up into equal groups. They use the word greatest in the question. When I do that, I find the common factors, and then I can talk about them with their factor pairs for how much I break it up into and how much is in each bag or package or group. All right, activity 5.1, calculating the greatest common factor. In the previous activity, you determined the greatest number of packages that Emily could make from 3 different types of beads. In other words, you were looking for the greatest number that is a factor of the 3 other numbers, 40, 72, and 24, and that's what we did. One way to determine the greatest common factor is to start by listing all the prime factors of each number. The table shows the prime factorization of 24, 40, and 72. The table is organized to show each prime factor in its own column. Analyze the table and circle the common prime factors. All 3 of them have a 2. All 3 of them have a 2. All 3 of them have a third 2. And then for the other ones, they don't all of them have a 3. They don't all have a 5. They don't all have a second 3. All right? So, done. Next, the greatest common factor is the product of the common prime factors. And so for this one, since they had 3 2's, the GCF is going to be 2 times 2 times 2, which will be, because they all share 3 2's. They all have that. And so that is going to be 8 for that particular problem. And so the greatest common factor here is 8, and that's where I should have written that down. What's the greatest common factor of 24, 40, and 72? And then 3 is like a trick question. What is the least common factor of 24, 40, and 72? The least common factor is always 1, because every number has 1 as its factor, and that would be the smallest possible one. All right? And now they want us to use the distributive property and the GCF, greatest common factor, so we need to use 8 to write the distributive property. And so I take that out, and 24 divided by 8 is 3, plus 40 divided by 8 is 5, plus 72 divided by 8 is 9. And so that is me using the distributive property and the GCF to rewrite this numeric expression. Oops. Number 5, determine the greatest common factor of each pair. So I could do this a couple of ways. I could list all the factors. I could do the prime factorization. 2 and 6, 2 and 18, 3 and 12, 4 and 9, 6 and 6, 1 and 48, 2 and 24, 3 and 16, 4 and 12, 5, 6 and 8, and that should be it. Okay. Then if I look at these, we have all our common factors. 1 is a common factor. 2 is a common factor. 3 is a common factor. 4 is a common factor. 6 is a common factor. 12 is a common factor. And that's the greatest one. So the greatest common factor is 12. 37 and 81. I know that 37 is a prime number. It's a prime number because its only factors are 1 and 37. For 81, I know it's 1 and 81, and then I know it's 3 and 27, and then it's 9 and 9. The only common factor there is 1. 37 and 81 are relatively prime to one another. Okay, that was that vocabulary term from the previous page. Now I want to rewrite each numeric expression using the distributor property and the GCF. So 12 was the greatest common factor of 36 and 48. So once I take 12 out, 36 divided by 12 is 3. And once I take 12 out, 48 divided by 12 is 4. So that's rewriting the numeric expression using the distributor property and the GCF. For 37 and 81, 1 is the greatest common factor. 37 divided by 1 is 37. 81 divided by 1 is 81. And so that is me rewriting the numeric expression using the distributor property and the GCF. Activity 5.2, using GCF and LCM to solve problems. Remember that common factors help you think about how to divide or share things equally. Common multiples help you think about how things with different cycles can occur at the same time. Okay. Raymond and Justine are watching different broadcasts of a parade on television. The broadcast Ramon is watching airs commercials every 17 minutes. The broadcast Justine is watching airs commercials every 14 minutes. Both broadcasts started at 7 a.m. and are scheduled to end at 9 a.m. When will commercials air on both broadcasts at the same time? Explain your reasoning. Okay. So I could list down the multiples of 17 or the multiples or keep time with this, which might make more sense here. I know that this is time, so it gets bigger. Okay, so this is one of those instances where we're looking at the LCM. Because time keeps going, it's going to go from this to this. I'm not splitting up 17 minutes into little parts. I'm adding 17 minutes on. I keep on adding 17 minutes on for Ramon. So according to this, 717. Then the next one would be at 734. Let's see here, I'm going to add 44, 54, and then take away 3, so 751. 61, 8, 11 minus 3, 808. Then we would have 8, 18, 828, 825, 35, 45, 842, 52, 62, 859. It's the last time there. If I've done this correctly, which I might not have. Double check my work. Justine, 14 minutes. So the first commercial's at 7:14. Second commercial's at 7:28. Third commercial's at 7:38, 42. Next commercial is 7:56. 06, 8, 10, 8, 24, 8, 38, 8, 52. All right, let me take a look here. So if I look at this, no, 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 no. The Commercials will not air at the same time. And if I was thinking about this a different way, I know that 17 is prime. I know that 14 is going to be 2 times 7. Okay? And so for my least common multiple, I need to have 2 and 7 and 17 in there to equal my LCM. Or in this case, 14 times 17 essentially. Okay? Let's see here, 17, 14, 8, 2, 6, 0, 7, 1, 8, 3. So I get 238 minutes before these two should happen at the same time. The broadcast is from 7 a.m. to 9 a.m., and that's 2 hours, and 2 hours is 120 minutes. So it's not going to happen for just under 4 hours, and the broadcast is only 2 hours, and that's why there will not be commercials airing on the same broadcast at the same time. Aw. Okay. Great. All right, so over here now we're going to have some more LCM and GCF problems. And so as we're doing this, the first one, number 2, two cyclists ride on the same circular path. The first rider completes laps in 12 minutes. The second rider completes laps in 18 minutes. Both riders start at the starting line at the same time and go in the same direction. If the riders maintain their speed, after how many minutes will they meet again at the starting line? Explain your reasoning. So it's time, and time keeps going, time keeps getting bigger, and so time is almost always an LCM problem. And so I want to go back and forth. So I'll start with the bigger number, and then I'll catch up. 18, 12, 36, and then 30. And so it looks to me that after 36 minutes, they will meet again. Okay. To help this out, I want to kind of think also 12 is 4 and 3, which is 2 and 2. So 12 is 2 times 2 times 3. 18 is 6, 2 and 3 is 2 times 3 times 3. And so the LCM has to have all of 12 and all of 18 in. So the LCM would have, there has to be a 2, and that covers this 2 and this 2. There'd have to be another 2 to cover this 2. There'd have to be a 3 to cover this 3 and this 3. And then there'd have to be one other 3 to cover this 3. And so we double counted the 3s, and we double counted that first 2. Okay? And so 2 times 2 is 4. 4 times 3 is 12. 12 times 3 is 36. Okay? LCM has to have all of each of the numbers in there. Number 3, Dr. Abramson, and her assistants are working on 3 different experiments using water. Each experiment lasts for 15 minutes. Once again, we're having time, so time is usually telling me that it's probably LCM. For the first experiment, the water level must be checked every 12 seconds. So first experiment, every 12 seconds. For the second experiment, the temperature of the water must be checked every 30 seconds. For the third experiment, for the third experiment, the color of the water must be checked every 36 minutes. In minutes, list the times. All 3 experiments will need to be checked at the same time. List the times all 3 Sorry, I'm just rereading a couple times. All right, so I'd probably start with the biggest number. So I know it's 36 and then it's 72. Then I go with this one, 30, 60, 90, not there yet. 12, 24, 36, 48, 60. Aw, that's the same, but it's got to be all three. Okay, so when we have three numbers, it's got to be all three. All right, 72, 84, 96, 108. And I have to go with this one, and this would really be 120, 108, 120. Got another one, so let's see about 36. So we're kind of going back and forth with them a little bit. Let's see here. 82, 92, 102, 112 minus 4 is 108. Oh, that one and that one are the same, but not that one. Plus 36. Let's see here. Plus 40. So 18, 28, 38, 48. Take away 4, 144. Oh boy. 120 plus 30 is 150. Aw. 144, 54, 64, 74, 84, 180. Ooh, we might have one. This one is 180. Then I'm going to go 132, 144, 156, 168, 78, 180. Joy. In 180 minutes, all three experiments will need to be checked at the same time. Okay. Next, the students of Mr. Michael's art class are decorating a booth for Harvest Day. They have blue cloth that is 60 inches long, gold cloth that is 48 inches long, and white cloth that is 72 inches long. They want to cut all the cloth into pieces of equal length. Okay. Cut is telling me dividing. Equal length is also another hint that this will probably be the greatest common factor. So time, or when something gets bigger, it's the LCM. GCF is when I'm cutting things down. I'm not getting anything more of it. I'm breaking it up into equal parts. So we're not buying any more cloth. This is what they have, and they have to break it down. Okay. Then, what is the greatest possible length of the pieces without having any cloth left over? All right. So I could list all the factors, or I could try to do the factor trees. 8 and 9, 4 and 2, 2 and 2. 9 can be broken down to 3 and 3. So 72 is 2 times 2 times 2 times 3 times 3. 48 is going to be, let's see here, I could do 4 times 12, 2 times 2, 2 times 6, 2 times 3. 48 would be 2 times 2 times 2 times 1, 2, 3, 4. 2 times 3. Okay. And then 60. 60 would be, let's see here, 3 times 20, 5 and 4, 2 and 2. 60 would be 2 times 2 times 3 times 5. Okay. So the GCF would be all of the ones that are the same in all of them. So if I look at this, they all have 1, 2. So I would put a 2 in a GCF. Then they all have a second 2. So I put a second 2 in the GCF. That has a 2, no 2, no 2. They all don't have a third 2, so there are not 3 2s in the GCF. Next, 3. There's a 3 here. There's a 3 here. And there's a 3 here. So a 3 goes in the GCF. Now, this one has a 3, no more 3s, no more 3s. This one has a 5, no 5, no 5s. So my GCF is going to be 2 times 2 times 3, which is going to be 12. Okay? And so 12 inches is the greatest possible. Now, if they make 12-inch pieces, for the blue cloth, which I'm writing with a pink pen, if it's 12 inches, 60 divided by 12 is going to be 5 pieces. I get the factor pair that goes with 12 to get to 60. For the gold cloth, which is 48 inches long, 4 times 12 is 48, so they would have 4 pieces of the gold cloth. And then, last, I have the white cloth, and the white cloth is 72 inches long. 72 divided by 12 is going to be 6. So they have 6 pieces of the white cloth. So I have to find the factor pair to answer that question. Okay, that is that page there. GCF, breaking it up, dividing it into equal parts, cutting it. LCM, time, getting more of something. The 2 examples here were time. All right, so number 5 here, boxes that are 12 inches tall are being stacked next to boxes that are 20 inches tall. What is the shortest height at which the 2 stacks will be the same height? So we're stacking. Since we're stacking, we're adding more. Since we're adding more, this is an LCM problem because we keep on going up by 16s and by 20s. Okay, so I could list them. And so if I list the multiples of 20 and I list the multiples of 16, that will get me to my LCM, my least common multiple. 58, 68, 64, 74, 84, 80. Now, since I'm really good at listing these, like I can go back and forth and I can get them. I know I was done because I got to a multiple of 20 and I knew that was a multiple of 20. And so 80, because it is the first multiple that appears in both stacks. Okay. Once I get to an answer I know, I want to try to do the thing that's harder, and probably for most of you, finding the LCM with the prime factorization is probably harder. And so, with that, if I make a factor tree of both of them, I see that 20 is 2 to the second power times 5. 16 is 2 to the fourth power. I have to have all of 16 in my LCM. I have to have all of 20 in my LCM. So I can have a 2 here, and that 2 can double count for that one. I can have a 2 here, and the 2 can double count for that one. And then I still need 2 more 2s for the 16. And then I need a 5 for the 20. Now I have all parts of the 20. I have 2 2s and a 5 at least. I have 4 2s for the 16. When I multiply these all together, I do in fact get 80, which is the LCM. Now, how many boxes will be in each stack? So for the 16, it'll be 1, 2, 3, 4, 5. It'll be 5 16-inch boxes. And then it will be 4 20-inch boxes. So it's kind of like which multiple of each number is what that's asking. Whereas on the previous page, it was saying if I divide it by 12, how many will there be of this kind of tablecloth or whatever the question happened to be. All right. 5.3, making connections. Recall that numbers that are relatively prime have no common factors other than 1. So we had that example on the previous page of 37 and 81. These number pairs can show interesting patterns. 1, for each pair of numbers, determine their product, their least common multiple, and their greatest common factor. Okay, so product, I can write the product for all of them. Product is just the fancy word for multiplying the two together. And for 12 and 10, it would be 120. For 9 and 10, it would be 90. For 9 and 15, it would be 135. For 5 and 9, it would be 45. The next one is the least common multiple. And I could list my multiples. I was looking for the first one that ended in 10. Or ended in a 0, sorry. And I see that that's half of that. Okay. For 9 and 10, I know what the answer to this one's going to be before I started doing it, because I'm old. 63, 72, 81, 90. Bingo. 10, 20, 30, 40, 50, 60, 70, 80, 90. So their LCM is equal to the product for that one. For 9 and 15, it will not be. 15 is 15 and 30. Then I'll go back and forth with them. I'm like racing them. 18, 27, 36. Then I'll do 45. The next one's 45. The LCM is 45 between these two. Okay. I know that this is 3 times greater than this. Then 5 and 9, I know the LCM will be 45, but I can go and list it. 5, 10, 15, 9, 18, 27, 20, 25, 30, 35, 40, 45, 36, 45. 45 is the LCM between those two, and the only factor they share is 1. All right. And so if I'm thinking about this, C and D are what they set up here, which is they're relatively prime to one another. They only have a GCF, greatest common factor, of 1. GCF of 1. So 9 has 1, 3, and 9. 10 has 1, 2, 5, and 10. The only one that's the same is 1. And so their LCM and their product are the same. 5 has factors of 1 and 5 because it's prime. Only has 2 factors, 1 and the number itself. 9 is 1, 3, and 9. It has 3 factors, and the only one that's the same is 1. And so their LCM is equal to their product, and the LCM is equal to 1. GCF, let's see here. 12, the factors are 1, 2, 3, 4, 6, and 12. For 10, the factors are 1, 2, 5, and 10. The GCF here between these is 2, and 60 times 2 would equal 120. There's a connection between these. The GCF between these two, let's see here. 9 is 1, 3, and 9 for the factors. 15 is 1, 3, 5, and 15. The GCF between those is 3, and 45 times 3 equals 135. So you can see how those are kind of related. Whoa. Mind blown. All right, so consider the GCF and LCM of the pair 9 and 10 and the pair 5 and 9. What relationship do you notice between the product, LCM, and GCF of the pair of numbers? Well, the numbers are relatively prime, so their GCF is 1. With both pairs of numbers, their LCM was equal to their product. And so it's like what I was talking about on the last page. Those two numbers only had 1 as a common factor, so that's the greatest common factor. And with both of them, the least common multiple was equal to them being multiplied together. Okay? Write a sentence to describe your conjecture. My conjecture is if two numbers are relatively prime, put in parentheses, their GCF is 1, then their LCM will be equal to their product. A conjecture is a tricky thing. It's kind of saying, we think this is true. This is something I think is true, and I can test it to start to find out if it still remains true. And I can keep on testing it. I don't know for sure. It's not a theorem yet, but I do know that it does stay true. Now it says, test your conjecture by determining the product, LCM, and GCF of additional pairs of numbers between 1 and 20. So if I took something like 2, which I know is prime, it only has factors of 1 and 2, and I took another number like that, such as 7, and I know its factors are only 1 and 7, I do know its GCF is going to be 1, like I said. I do know that its product is going to be 14. 2 times 7 is 14. I do know that if I list the multiples of 2, 4, 6, 8, 10, 12, 14, I do know that the LCM is going to be 14 as well. Okay, so that partially proves it. I can do one more example that is going to show me that it's the opposite case. So let me say I take 3 and I take 6. Okay, the GCF of 3 and 6 is going to be 3. The factors for 3 are 1 and 3 because it's prime. The factors for 6 are 1, 2, 3, and 6. The product of 3 times 6 is going to be 18. And then if I list the multiples of 3, the LCM is going to be 6, which 3 times 6 equals 18. Or I could think of the GCF times the LCM will always equal the product. The GCF times the LCM will always equal the product is another way to think about this. I kind of like that as a conjecture as well. Mind blown. All right, talk the talk. In summary, answer each question to summarize what you know about greatest common factors and least common multiples. 1. Can you always determine the greatest common factor of any two numbers? Explain your reasoning. Yes. All numbers have factors, or all numbers have 1 as a factor. So, even if they don't share any other common factors, one will still be a common factor. If the greatest common factor of two numbers is 1, what can you say about the numbers? Okay. Well, what they kept on putting in there is the numbers are then relatively prime. And we just learned, or I just learned, that their LCM will be equal to their product, which is like a common multiple of any two numbers. Explain your reasoning. Yes. Even if they don't share any factors but 1, they will have a common multiple which will be their product. If the least common multiple of two numbers is the product of those numbers, what can you say about the two numbers? That they are relatively prime. Which means they don't share any factors except for 1. How can you use the GCF and the distributive property to rewrite the sum of two numbers? Okay, well, you factor out the GCF, then you use the factor pairs that go with the GCF. So, if I was to take, I don't know, 6 plus 14, the GCF of those two numbers is 2. So you factor out the 2. Then what goes inside is the factor pair that goes with 2. So 6 divided by 2 is 3. The factor pair is 3. 14 divided by 2 is 7. And so that is how I factor out the GCF and use the distributive property to rewrite the sum of two numbers. La cucaracha, da 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 da.